So today I'm going to be talking only about IcedCoffeeScript, TameJS, though the same thing really is just a different flavor, of these ideas. Okay, so I have three major goals today. First is I want to convince everyone that there is a problem to be solved, because there's a little bit of debate on that point. And then once we've agreed that there's a problem, I want to talk about the types of solutions or the specs of the solution, and also show you a little bit about IcedCoffeeScript and how it meets the spec of the spec to solve the problem. Okay, so I'm going to jump a little bit between like browser code and node.js code, but everything works in both cases. So is everyone somewhat familiar with CoffeeScript? Can you guys read this okay? I'm trying not to get too deep into like the really nitty-gritty features. This is just a function definition, a nice CoffeeScript. And it's doing this. It's trying to take a term of your choosing and to do a query and to query Twitter's JSON API to get there like some search, like JS-conf.eu or whatever. And then it's going to use the jQuery JSON P library, and when it has a result, it's going to just call a callback with either the results or maybe null if it failed. So you might be looking at this and say, well, I know this is a regular type of CoffeeScript or JavaScript flow where the code's starting on the upper left and going to the lower right. It's not that big a deal, right? This is, this is your code pyramid, and everything's flipped in this in terms of the black and white. So that's supposed to be the pyramid in Egypt with the Sphinx in front of it. So that's like the code of death, the pyramid of death. So this problem is manageable. You can deal with it. The question, though, is what happens when you start building real, more interesting programs with that type of call in the middle of it. And so here's an example of something I wrote to show a table of items. So you can imagine I have an array of 20 items, let's say, and I wrote a little loop, and this is fine. This code works OK. For each item in the list, it's going to go through and write the item out to your browser. And if there's enough room on the line, like if it's like a small word, then there's room to show an ad. So we could show an ad there and then go to the next row. So this works fine. But let's say we decide to make a change to our code. And instead of just showing the ad, we want to make the application more better for our users, and we want to actually show the result of a Twitter search where that ad used to be displayed. So now, if you recall in the first slide, I showed you a search function. And the second parameter of that search function was the callback that search was supposed to call when it's done with its computation, right? And so I just wanted to swap that in for my showing the ad, but I have no idea what to put in place of the question marks. And really, what I put there is this horrible realization that I have to rewrite my code. So I'm not going to rewrite this function, but if you were to rewrite it and do it the right way, you would totally change your while loop into something that looked nothing like a while loop whatsoever. So you'd have a crazy callback pyramid of death, and at the bottom of it, you'd call your callback. So just imagine I went ahead and did that. But now we go one layer up, right? And so what's happening to the code that actually called this show table function? Well, just imagine it's this function that writes a whole page. So the first thing it'll do is it'll show a header, and maybe it has a left bar. And on the left bar, it'll show this awesome table. It'll show a main page, and maybe it has a right bar. And on the right bar, it'll show this awesome table, and then it'll show a footer. OK, well, that was show table the first time I wrote it. What happens if we change it? So again, show table has now been changed. So after it's done its computation, it's going to call its callback back. So I actually rewrote this. And just to show you what this very simple 5-line program looks like, it changed into this. And I don't think there are any bugs in there, but I don't really know. And I could have easily left out one of the branches. So I'm sure everyone's familiar with this type of thing, right? And then it's all, well, sorry, that's 3 turtles on top of each other. So it's turtles all the way down. So you keep doing this all the way up your stack, and you have to rewrite your whole program just because you want to change one inner function. And if this sort of thing is interesting to you, there are other great activities you can consider, like hand factoring large numbers, hand inverting large matrices, and hand assembling x86 code. So there is a problem here, and that in a very simple JavaScript case that shows up all the time on the browser or Node.js, we're asking humans to do the job that compilers ought to be doing. So I think we all can agree that that's not a great state of affairs. OK, so I want to talk about how to solve this problem. So the first thing we need to do is what I just described. We need to find a way to do an automatic continuation passing style conversion. That's what I just was describing the problem as, and we'll talk about what that means. But there's really 3 other requirements, too, that we need. Since we're going to be changing the language or adding new features to the language, we want to employ an economy of mechanism. I'll go over that on the next couple slides. We want it to be backwards compatible, obviously, so we can use it in as many places as possible. And finally, we don't want to sacrifice the power that JS is giving us. So I'll go over all 3 of these in more detail. So what do I mean by economy of mechanism? So if you look at JavaScript or if you look at IcedCoffeeScript, you already have these great tools. You have like if, else, and for, while, and you don't want to get rid of those. You don't want to like replace those with this new library that's trying to do what these things already do for you. So you want to keep those great mechanisms, and if possible, add as few new keywords as possible. So in this case, I say only a 2 at most. You don't want to make the language fat with all its features that sometimes you don't even need. By compatibility with all APIs and libraries, JavaScript has obviously been around for a while in lots of different contexts. And there's very little agreement among people who write libraries or JavaScript engines as to what a callback is supposed to look like. Is it supposed to be the first or the second parameter? And what are the parameters to that callback? And so here are 3 examples that all seem to be at odds with each other. There's the set timeout function that everyone uses, and there's the jQuery getJSON call. And if you look at that, the callback is the 3rd parameter, but the data comes first and then the status. And then finally, the 3rd example is the request package, the node package written, that's the most popular node package in NPM. And you can see there the error comes first, and then the response and the callback. So obviously, whatever we do to address this CPS conversion, we can't take for granted that callbacks happen in a particular place and that the error is a particular place within the callback. And also, I mean, we want some solution to work with all runtimes. So V8, Spider Monkey, and we also want it to work on the browser. And so the only way to do that is with source-to-source translation. And I mean, CoffeeScript is such a natural case for, language for this, because it's already doing translation as it is. The question is, can we just add a couple more translations to get the features we want? And the last point is a little bit subtle, but you could do a lot of really cool things now with hand-rolled JavaScript, right? You could very easily fire multiple parallel calls and get answers back whenever you want to. You can do things like, and you can do that both in the browser and in Node. You could do things like even more complicated, like pipeline flows, what I call. And so that means, let's say you have a list of 100 requests to make, and you only want 5 of them to be outstanding at once. You could do that with JavaScript, and it's a little bit complicated, but it's definitely possible. And finally, you could do interesting things like short-circuiting slow operations, and you could have functions that do background work, like they call their callback first, and then they do some other stuff. So these are all great features of JavaScript that we do not want to delete. We want to preserve them, JavaScript and CoffeeScript. So we want to preserve these in our new language. OK, so just to give you a preview of what I'm going to show you about IcedCoffeeScript, here's my example where, remember, we flipped the whole function. We flipped the whole function upside down. We didn't know what to put there to preserve the structure of the code we had. And with IcedCoffeeScript, really, we can preserve everything and just make a small change and keep going on our merry way. So I'm going to tell you exactly how this works. OK, so Ice starts with regular CoffeeScript and just adds 2 new keywords. The first is defer. It's a lot like a regular function, but it has some special features, so it has to be a keyword. And the second is this await keyword, which alters control of your program. So it's a lot like for or if, where it's actually going to change the way your program runs. OK, so first I'll talk about defer. All defer really does is it makes a callback for you. So you call defer, it returns to you a callback. And as usual, once you have that callback, you can then do whatever you want with it. So in this case, you can pass it to a callee function. The callee will do whatever it has to do, and when it's done, it'll call its callback. It'll tell the caller that you can now proceed. So defer is a function that returns a callback. And defer works very well with this other keyword called await. And here's what await does. it's a block of code. So I've given an example here. And control enters the await block, and it executes every last line of code as normal, but it waits at the very end of the block before proceeding. And what's it going to wait for? Well, in this case, our await block has an unknown number of defers depending on whatever code is, whatever the value of x is, and whatever the value of y is. But let's say you enter that if statement, and you go through the while loop 3 times. So you'll have made 4 defers. So control will block at the end of the await function, at the end of the await block, until all 4 of those callbacks generated by defer have triggered. So it's a way to stop your program until you have an answer to things you need to proceed. So once all that's done, then you can go to BAM and go on with your program. So here's the most basic ICE example I can come up with. It's something that you just wait a second and then print. So I'm using the standard setTimeout function. And setTimeout, as you know, takes a callback as its first parameter, and that's the callback that it calls after a second of waiting. So in this case, this is an await block that's just been moved to one line, but it's an await block that has one statement, which is call setTimeout. When setTimeout fires its callback after a second, control can proceed past the end of the await block into the console.log hello. So this waits a second and then prints hello. And just to show you a little bit more complicated example how callees and callers interact, I prepared this other one, which is really just going to print 1, 2, 3, 4, 5. But it's with 2 different functions now, f and g. So let's say you start with f. The first thing that will happen in f is you do a console.log to print the number 1. OK? Now we go into the await block in f, and what that's going to do first is call this other function g with a callback generated by defer. So within g, now we're in g, the first thing we do is print a 2. And then we're going to, as in the first example that I showed you, we're going to wait 10 milliseconds for a timeout. So at this point, control cannot proceed any further in G. So it jumps actually back out to F, because F can still keep doing other things. It hasn't reached the end of its await block yet. So it's going to then print 3, and then control will jump to some other part of the program. After that 10 millisecond timeout expires, we can now proceed in function G, because all the defers within its await block have finished. And then G can call its callback. Now what happens when G calls its callback? Well, that allows F to proceed past its await block, because it only had 1 defer in its await, and now that's triggered, and so now we can finish F. And just to briefly describe to you how this can fit any API you can dream of, I haven't shown this to you yet, but defer actually takes arguments. And the arguments of defer are the arguments to be filled in by the callback when it's actually called. So that's why defer isn't actually a real function. It's actually implementing something a little bit like pass by reference in C++. So after control leaves this await block, the request library will have filled in the error and the body, and they'll be available as those two functions. So in this way, you can use IcedCoffeeScript in any API. OK, so I've told you about automatic CPS conversion in IcedCoffeeScript. I've told you about the economy of mechanism, hopefully, because it's only 2 new keywords. I told you about how to make it compatible with all existing libraries and APIs. And the only thing I've left to show you is how this makes for really cool programs that have interesting control flow. OK, so let's talk about the one we looked at in the first series of examples, which is just a set of serial calls. When one finishes, the next can start. And this is what it looks like in IcedCoffeeScript. So let's say we have a series of 20 terms we need to search for from Twitter. What this loop will do is it'll loop through each of those 20 terms one at a time. And on each one, calling this search function that makes a Twitter call. And then it populates the result into that slot in the result array. So this is just for each item, wait for that thing to finish, then do the next item. Done. The really cool thing is, how do we change this into a set of 20 parallel calls? Well, it's a minimal change. We just switch the order of the await and the for loops. And so now if you look at this, within the await block, we're going to be doing a whole bunch of things. We're going to fire off 20 different requests at once. And once all of them have completed, then we're ready to continue. So this is how you would implement parallel control flow with IcedCoffeeScript. And this gets slightly more complicated, but it's a little bit more code. but it's the same ideas at play. I wrote this little class called a pipeliner library, and that's using just regular IcedCoffeeScript that I've described to you so far. It's not on the slide, but it's in GitHub if you want to check it out. And what does this pipeliner do? Well, it tries to enforce network flows with only a certain number of requests outstanding. So in this case, there are only 5 requests outstanding, even though we might have 1,000 different terms where we're going to query. And so here's the way it works. With a pipeliner, you wait before you launch your call. So if you go into this loop, the first thing that'll happen in the loop is that you'll ask the pipeliner, is there room in my window to fire a call? If yes, you'll go right past that await block. If not, you'll be queued up until the next guy comes back. So in this case, when that 5th outstanding query comes back, I now have room in the pipeliner, so I can keep going. It'll basically say I can go past the await block in the loop. And now, when I need to generate a callback, I actually need to ask the pipeliner for the callback, because as I told you, there's a little bit of accounting going on here, and this pipeliner class needs to know when is it that I can launch the next guy. So the pipeliner actually has a defer function, which I've implemented with this regular IcedCoffeeScript, and it's doing both the accounting and also populating the result, as we saw in the previous slides. And at the end of this loop, I have to flush to make sure that all 5 outstanding guys are back, and then I'm done. So this is a pretty complicated control flow that's just very succinctly captured with this library. And I told you something about doing background work. So when you're in this asynchronous idiom, you're past a callback. Your function's past a callback, and you call that callback to tell your caller you're done with your work. But it doesn't mean you get to stop executing. And in particular, let's say I want to take this search function I've been talking about, tell whoever's doing the search that, OK, I got your result, go print the page. But then I could do other things like save to disk or, I don't know, do something else in the background. And this is also possible with IcedCoffeeScript. In this case, after I've done a search, I call back my callback with the result. Here's your result. Then I can save the file to disk and then report an error or something. So just because you call your callback doesn't mean you're done. You could do a lot of interesting things. And this is a very powerful feature of a language. It just allows you to basically, in threads, you'd have to do something like call fork. But in IcedCoffeeScript, it's just a natural extension of the way things are laid out. And this last example is a little bit of a trip. It's allowing you to take any function you can think of, in this case our search, and apply to it a timeout. So if Twitter is slow, I don't know why that would happen. You could say either give me the result of the search, or wait, or if a second expires and I haven't gotten it, then keep going. And this timeout function is something I wrote with IcedCoffeeScript too. It's pretty interesting. It sets up 2 different racing computations. It sets up a timer that's going to go off the amount of time you ask for, and it sets up the Twitter search. And whichever one of those comes back first will then allow you to exit this await block and keep going. So what that really implements is a timeout. Either I wait a second or I get a result, but not both. So again, this is a little bit of magic that's hidden in a library that I wrote, but the library was all with IcedCoffeeScript. So again, it's part of this composable language with just this with this natural set of features that allow you to do very interesting things. So how is this all pulled together? As I promised, I didn't want to change the interpreter. I didn't want to do things like require fibers because that's not portable across all different implementations. So really what I wanted to do is take a CoffeeScript and do more or less a source-to-source translation. So the way this works is you parse CoffeeScript as usual, you get the abstract syntax tree, and then you do a rotation on that syntax tree to actually implement the continuation passing style translation. And then alter output code, and then output code mainly as normal, but with some differences for the things that you rotated. And so I'll explain to you what a rotation means. So here's a very basic example. Function F2, function F1 is called, I'm awaiting on F2, and then after that's done, I can call F3. So here's the regular syntax tree for that, as would happen with the vanilla CoffeeScript compiler. There's just a block that contains F1, a subblock that has a wait with sub-subblock of F2, and then F3. But in a rotation, you have to change what's the child of what, because this F3 can only be called at the await node's discretion. So what that means is we're going to take that third arm of the tree and basically make it to be a child of the await block. And this is more or less a rotation. So as you can imagine, this has to be done recursively up the tree. So everything that within an await block needs that type of rotation. Parents of those nodes need rotations. And also inside of loops, things get a little bit interesting. If you have break or continue inside of a loop that also has await blocks, then you have to do rotations inside those loops. But a key thing that I've discovered is you want to use this sparingly. You don't want to do this for every possible node in your abstract syntax tree, because things will really explode on you. So with a little bit of care, you can decide only which nodes need to be rotated and just apply those rotations to those nodes. And this helps keep the code as clean as possible. So finally, I want to tell you a little bit about how this was implemented. I didn't rip up all of CoffeeScript. CoffeeScript is about like a 5,000 line program, and it turned out I added about, let's say about 1,500 lines of code. In particular, the grammar and the lexer file in CoffeeScript barely changed at all. So these were very simple changes to the grammar and lexer. Kind of all the goods are really within this nodes.coffee file, in which the output code is emitted. And finally, so I think I've covered all the interesting parts of Iced, and I've tried to tell you why Iced is meeting the spec for how to make interesting asynchronous and simple programs with JavaScript and CoffeeScript. One last thing I want to say is that this isn't just a toy project. We've actually built a real site with it. It's in the wild. And there's a little asterisk next to it because this site is in private beta right now. But it's this site called Composable, which we're trying to develop a matching system based on people's interests. And it's about 30,000 lines of IcedCoffeeScript with about 10,000 lines of Go code. But just to give you a sense of how that breaks down with our new keywords, it turns out about 2% of those lines use these await blocks, and about 9% of those await blocks are using more exotic concurrency than just straight line A, then B, then C. So we're actually getting a lot of use out of the power within the library. And even this pipeliner class shows up 20 times. OK, so there are my turtles again. They're flipped negative. But the next time you have one of those oh god no moments where you have to rotate your whole program, just remember, use CoffeeScript, use IcedCoffeeScript. It'll save you all the hassle. And really what I want to do is try to get a grassroots movement to get this code mainlined into CoffeeScript. So far, there's not really enough support, but I encourage you guys to download it and champion these new language features if they actually solve your problems. And with that, hopefully there's a couple of minutes for questions, and thank you for listening. Yes.
So how do you realize the await block waiting? Does it actually yield back to the browser and get called back? Or are you blocking somehow JavaScript itself?
No, I could maybe try to show you the rotation really quickly. I don't know if I could pull it up. Can you see that? No. Anyway, the answer is you take the code that's supposed to come after the await block and you package this up as a function. And now that function can be called whenever you're ready to do it. So there's a little bit of code in await that says, roughly the answer is, let me just backtrack. OK, you have the rest of the program as a function, and you basically pass that as a callback to set timeout in this case, and then just fires for us. So no changes to the browser.
What's your experience with debugging this stuff? What does it do?
OK.
How do you rationalize what's happening?
So this is a great example as to why, in some cases, we're better off. And basically, we can annotate this code. So people already have this problem anyway with hand-rolled callbacks, because you'll get a return from Twitter, and the whole top of the stack will be lopped off, and you'll just be left with a couple frames above the Twitter search returning. And so actually, because we've made this a lot more structured, you can now annotate the code and kind of recreate the chain of callbacks that got you to where you were. And we're able to say, this actually happened at, this is on the GitHub page. I'm not going to be able to explain it. But it'll tell you the real set of calls that actually wound up there. And we could also do something like use real line number translation as opposed to CoffeeScript the CoffeeScript to JavaScript translation. So anyway, I think the answer is it's better at debugging because it's a more structured way of putting your programs together. Yes, back there.
So what was your process at arriving at this solution to the problem you talked about at the beginning? Was this organic? Like how did you get there?
We got there. We had done the same thing in C++ in about 2007. We started with the same problem though. We had a whole website built with C++ hand-rolled callbacks, and that turned out to be, I mean, people were like quitting our company because they just could not deal with it. So we decided we had to come up with a better solution. And the solution we came up with was one that had all those 4 requirements that I spoke about, and it had to be backwards compatible because we couldn't rewrite the whole thing from scratch. So these primitives kind of fell out of that, and it turned out they're exactly the same thing that works, in my opinion, really well for CoffeeScript and IcedCoffeeScript. So I guess experience is really how we came up with it.
Okay, I think that's it for now. So if you have any more questions, Max will be available.
All right. Thank you,
afterwards.
everyone.
So thanks very much, Max.